You're welcome to MTH 306. We're now in the second part of chapter 2, and in this video we'll be considering two theorems, the Cayley's theorem and the Cauchy's theorem. Okay, so we begin with Cayley's theorem. Now, if you recall, in our last video, I had pointed out that we needed to know a particular theorem, theorem 3.13, by heart, because I'll be using it later, and I'll be using it in particularly for Cayley's theorem today. So, well, in this video. Okay, so Cayley's theorem states that any finite group G is isomorphic to a subgroup of the symmetric group of order n, of degree n, where n is equals to the order of G. So if you have a group, Cayley's theorem is saying that whatever the group is, it is isomorphic to the symmetric group, okay, of degree n, okay, where n is the order of the group G itself. Basically, you can relate it to the permutation groups, like, okay? Okay, so the proof goes that in order for this to happen, if you remember, when we were considering group action, we had a map of this form that mapped into the symmetric group on the set homes, right? Okay, so we'll be using that idea and concept in the body of this proof. Okay, so we let G act on itself by multiplication, so which is your regular permutation, if you recall the definition of a regular permutation. So it's going to act on itself. It's going to act on itself by right multiplication. So we have GH, okay, G is acting on itself. So we have G and then H from G. So it's going to act on itself by right multiplication. So you see that the H is on the right of G, right? For all GH in capital G. Now, by the concept we had alpha G equals to alpha, right? For our permutation, sorry, for the group action. Now, alpha G acting on itself, sorry, GH acting on itself by right multiplication means we'll have something like this, right? Now, if it turns out that G with H acting on G gives us G again, what does that mean? It means that something happened to the value of H. It's not there anymore. It means H goes to 1, right? That tells us something. It's a function, because we are talking about the symmetric group, right? So before we talk about functions, once H goes to 1, something about it is quite canny, right? Anything that goes to 1, like I told us in class, seems to be something that has to do with the kernel, right? So by the definition of the kernel, it implies that H lies in the kernel, right, of the group action. And we have defined the kernel of the group action already. Well, so simply we start by letting G act on itself by right multiplication, and this is how it looks like. We check what happens when it goes to G, more like we're checking the stabilizer, right? And we get that H goes to 1. If H goes to 1, it means it lies in the kernel by definition of kernel automatically. Now that we've done that, we have our definition of our kernel. We know what the function of the relationship with the group action looks like in G. The next thing we need to introduce is the mapping. This map, which I had mentioned earlier, and which we had stated in a theorem that I told you we needed to know by heart. That's theorem 3.13, the second part of it. That theorem states that the mapping rule, which maps the G into the symmetric group on the set homes, defined as you can see on the screen here, for any G in a small letter G in G, is a homomorphism. And by the first isomorphism theorem, so we picked this out from that, from the second part of theorem 3.13. And now I recall in our last class, the one on not the last class, but the one on direct products, right? We had noted the first and second isomorphism term, right? So here we need the first isomorphism term. The first isomorphism term states that you have a homomorphism theta that maps G into G prime of groups, then G modulo the kernel of theta is isomorphic to the image of theta. So that's what you have on the screen right now. So we're going to be using these two key theorems to continue. Okay, so it follows that we seek a map rule, right? Because that's what the Cayley's theorem states, that we have an isomorphism from G into the symmetric group of order n or degree n. So we need to get a map that will take us and relate us to the symmetric group of order n. Now we know what the group action looks like. We already know our kernel contains H, and H is already equal to 1, which means our kernel is basically the identity 1. We have found the map that satisfies a homomorphism and maps G to the symmetric group on the set Holmes. Our own symmetric group is a set of symmetric group of order n already. So that's the map we have here, right? Okay, so what do we do next? Now, since the map is a homomorphism, we have by the first isomorphism theorem that G modulo the kernel of rho is isomorphic to the image of rho, right? Because we had rho, okay, there, since this is our term, right? We know that for the first isomorphism theorem, it says that G, let me clean this so that's not too, we have that theta maps G into G prime, and that the G modulo the kernel of theta is isomorphic to the image of theta, right? So if we have this, our map now is rho, right? There it is here. Our group is G, so it works well. So since it's rho, our theta changed to rho, that's why we have rho up here. So you can see G modulo rho. Isomorphic to the image of theta, so this is the image of rho. So instead of theta, we have rho here. So comparing all of this with this, okay? So that's how we arrived at what you see there. Okay, so with that said, we know our kernel of rho. We got it that contains H, and H was equal to 1, if you remember, if you recall actually from here. Okay, we had that the kernel, H lies on kernel, and definitely it's going to be equal to 1, right? So we know what our kernel is. So now by asterisk, which is what I just left just now here. So by asterisk, the kernel of rho is just the identity. So what happens to G modulo the kernel of theta? It will just give us back G, right? So we've gotten G. So now it means that all of this is now G, and this remains the same, right? Okay, so with that, we have G, and all will be a subgroup of image of theta will be a subgroup of symmetric group on the set Holmes. Hence, this is satisfied, where Holmes, the symmetric group of the set Holmes, is just simply S subscript n, and that's all to the proof. Okay, so this particular theorem relies on the definition of group actions, regular group actions, relies on your knowledge of the first isomorphism theorem and definition of the kernel, and then you apply, compare the two results, and then you conclude. Okay, the next thing I need you to know before we go into the Cauchy theorem, which is the next theorem we're considering, is this mathematical identities. Now, in group theory, whenever you have that basically cyclic groups, that when you keep going and you get A up to B and you get your identity, it means it brings you back to 1, basically bring you back to the starting point. It means that the number of A's you have is actually going to be B. Okay, so the order of A, numbers of A's, number of A times you go repeatedly. So you have A going 1 till you get to A, B 2, and keep going to A to B, and you get back 1, means you're starting at the beginning again. So basically it's a way of counting. Okay, so once you have this identity, whenever you have A raised to power B equals to the identity in group theory, it means that the number of A's in that group or set is B. There are B of them. Okay, so with this knowledge, we want to apply some indices. Now you know this as our standard. So we want to apply some indices. Now it means if I have A raised to power M, I'm changing now. Instead of B, I put M. What does that tell you? It means that the number of A's will be M, right? Equals to 1 whenever equals to M, right? What if it is X raised to power Y and everything raised to power B equal to 1? So you can see it's changed. So instead of A raised to power B equal to 1, right? You're having, and this we say means that the number of A is B, right? It means in this case here that the number of X to the power Y must be B, right? So that's what I've written here. That's what I've checked here. I'm bringing us somewhere, so don't just keep following and getting an understanding of what I intend to show us, because we'll need this manipulation later. Okay, now we still know that if I have A to the power B and it gives me 1 in group theory, that means that the order of A, number of A's, there are B of them. What if I happen to have that the order of X is equal to P to the power A? So how do you go backwards? So when I have the order of A to be equals to B, it means that A raised to power B is equal to 1. I have the order of X equals to P. It means that what? X raised to power P to the A, P raised to power A equal to 1. I believe that's straight. It's easy to see, right? Okay, so don't get confused. We're going to use all of these things I'm writing shortly. Okay, the next thing I would introduce, because I did introduce it, or we did introduce it, because it's not my proof, it's someone else's work, I'm only teaching it, is this manipulation I've done here. Now watch. P raised to power A. Do you agree the same thing as P raised to power A times P raised to power, oh sorry, my screen is blocking me from typing, times P raised to power 0? But P raised to power 0 is 1, right? Okay, so do you agree that the same thing as P raised to power A times P raised to power minus 1 plus 1? Because minus 1 plus 1 is 0. I'm sure you've seen that. So do you agree indices allows me to do this? P raised to power A times P raised to power minus 1 times P raised to power 1. And you see that? That's what is here. This same indices allows me to do this. P raised to power A minus 1, everything times P, which is what you can see here. I only dropped the 1 P raised to power 1, so that's what you see here. Okay, so this same p raised by e can be expressed as this. Is what we're trying to make you see, simply by bringing in p raised by 0, which is same as this, which can be broken and factorized, as you can see on the screen. Okay, now you know this. Again, you can pause the video, go back, rewind, try to understand what it's saying. Let's go into Cauchy's theorem. Now, Cauchy's theorem states that if G is a finite group, so you can count the number of elements in G, and P is a prime divisor of G, of the order of G, that means that you have a prime number P, and that P, that prime number, can divide the number of elements in G, then G contains an element of order P. So there's an element X or M or whatever element you want to call it, whose order, when you count the number of elements, the order of that element, it will be P. Okay, so let's check how to prove it. Now, first and foremost, we need to find out if there is even a subgroup in this G, this group G, that has order P, so that we can now keep going down small till we get to the element, right? Now, remember Taylor's theorem, which was in our last video. I told us to know it by heart. It told us that there exists a silo P subgroup. Remember, we had defined silo P subgroup, we had defined P subgroups and P group itself, right? So now, Taylor's theorem tells us that indeed there exists a silo subgroup H of G. So if there's a silo P subgroup, it means that definitely that group, because it's a silo subgroup, so, and since, a silo subgroup, I won't call it a silo P subgroup. We know there exists a silo subgroup first and foremost by Taylor's theorem. And since P, because there's a condition here in the theorem, P divides the order of G. Since P divides the order of G, we can take the order of H. So there's a silo P subgroup, silo subgroup H. So we can take the order of H to not be 1, because I would rather call it a silo P subgroup at this stage, because Taylor's theorem allows me to do that, right? So let's take it that there exists a silo P subgroup H. And since the order of H is not 1, because it's a silo P subgroup, meaning that P divides the order of H, it means that the order of H cannot be 1, because P divides the order of H, right? So now, we can choose X and H. Like I said, we're going to start, we have the big group G, we seek an element X whose order is P, right? So we pick the big group G, we find a subgroup, so let me clean the screen so that I can explain what I'm doing. So we want to find an element. So we pick the group G, we know P divides the order of G, we get a subgroup H, and then we're seeking a small element whose order will be of order P. Okay, so let's continue now. So now we know that H is order P, it can be 1, so we can pick an element X in H because it's not empty, right? Clearly, whatever X we're going to pick, we don't want it to be equal to 1. Then the order of X definitely divides the order of H, right? That is true, because like I said, X is an element in H, so its order definitely must divide the order of H. Okay, now that we know that the order divides the order of H, and we know that the order of H is some prime P, right? For some R, we don't know what R is, so we know what the order, because it's a silo P subgroup. So definitely X must be of order some P. We don't know what power the P would be, so we called it A for some positive integers A, because we're picking X in H, and the order of H is this. So if X is in this, its own order will be some form of P with some power A, right? Okay, so now we know that so I'm now bringing in that notation. We want to find that if this X, if somehow we can find that X that is of order P. Okay, so we want to find it. Okay, so now we had seen in the previous slide that if we have A raised to power B and it goes to 1, then the number of A's will be B, right? That's what we have here. We had shown that in previous slide here, right here. That's what we had shown here. Okay. So now, the order of x, we said is p raised to power a. Can you remember? I had shown us here. So if the order of x is p raised to power a, it means that this is satisfied based on this argument I had shown us, right? So now you can see where I was coming from, or coming to. So now we know this, the order of x is this, because it's a subgroup of the order of h. So the subgroup of, it's an element of the subgroup h, okay? So it follows that we have this identity, okay? But we seek that the order of that element be p. That's what Cauchy's theorem wants. It wants it to contain element of order p. But clearly this order is not of order p, but order p raised to power a. We want order p. So how do we get that? Well, moreover, if I break this power, let me clean it so you can see it well. Oh, sorry, isn't the wrong thing. Let's clean it so you can see it well. We want x, the order of x, to be p, not p raised to power a. We don't want the a. So how do we remove the a? See how we do it. So what happened? X raised to power p raised to power a. I brought in the p raised to power 0. Can you see it? If you remember what I wrote previously here. Okay. See what happened? We know this. Then the p raised to power a, we brought in. So it was p raised to power a, became p raised to power a times p raised to power 0, which is 1, and then became p raised to power a times p raised to power minus 1 plus 1, which is 0, right? And then it breaks to p raised to power a times p raised to power minus 1 times p raised to power. So it became p raised to power that, which you can see on the screen. So we can now write this as you can see here. And finally we get it to be equal to 1. You understand? Because this is equal to 1, right? So all I've done is to change this part of it, which is all of it here, with the powers in place. So with this said, clearly it means that this, the order of this, will be equal to what? It will be equal to 1. Sorry, what am I saying? So we have found an element of G. So this is an element of G. So the order of it would be equal to P, right? So G contains an element x raised by P raised by A minus 1 of order P. So that's what we were looking for. We wanted the order of the element in G. So how did we get the element in G again? Like I said, we started with G, we got a subgroup H, and we considered an element X, which was in its subgroup. So this element is actually contained in G, and we're able to show that the element, when raised by P raised by A minus 1, its order will be P. So that's all to the proof, and that's all to Cauchy's theorem. I hope you have an understanding and can prove it on your own by the time you go over it. I will take it again in class, but for now you can go ahead and study the video. Okay, again, these are materials you can go through for the research, and thank you.